Hello everyone, my name is Ahllysa from Ejercito, and today we will talk about what is subnetting. So for this lesson, our key points are what is subnetting, subnet and subnet masks, and I'm going to show you an example in calculating subnetting. So what is subnetting? Subnetting is a technique that lets network administrators use the 32 bits available in an IP address more efficiently by creating networks that aren't limited to the scales provided by Class A, B, and C IP addresses. With subnetting, you can create networks with more realistic host limits. So, subnetting also provides a more flexible way to designate which portion of an IP address represents the network ID and which portion represents the host ID. With standard IP address classes, only 3 possible network ID sizes exist, which are the 8 bits for Class A, 16 bits for Class B, and 24 bits for Class C. Subnetting lets you select an arbitrary number of bits to use for the network ID. So, in subnetting, it can be any bits, whether it may be 26 bits or 20 bits or 22 bits, you can do so in subnetting. So also in subnetting, there are two reasons for people to use subnetting. So first is to allocate the limited IP address space more efficiently. So you can see in IP address, there are only limited space. So we have to use it efficiently, wisely. No, we have to just distribute it efficiently. So if the internet were limited to Class A, B, or C addresses, every network would be allocated 254 or 64,000 or 16 million IP addresses for host devices. Although many networks with more than 254 exist, 254 devices, few exist with 64,000, let alone the 16 million. So unfortunately, any network with more than 254 devices would need a Class B allocation and probably waste tens of thousands of IP addresses. And so the second reason is that even if a single organization has thousands of network devices, operating all those devices with the same network ID would cause the network to slow down or to crawl. So that way, TCP/IP works dictates that all the computers with the same network ID must be on the same physical network. The physical network comprises of a single broadcast domain, which means that a single network medium must carry all the traffic from the network. So for performance reasons, networks are usually segmented into broadcast domains that are smaller than even Class C addresses provide. So next, subnet and subnet masks. So a subnet is a network that falls within a Class A, B, or C network. Subnets are created by using one or more of the Class A, B, or C host bits to extend the network ID. Thus, instead of the standard 8 bits or the 16 bits or 24-bit network ID, subnets can have network IDs of any length. So here we have our figure 1. So this shows an example of a network before and after subnetting. So in the unsubnetted network, or the one before subnetting, the network has been assigned the class B address, which is the 144.28.0.0. All the devices of this network must share the same broadcast domain. So, in the second network, which is after subnetting, the first 4 bits of the host ID are used to divide the network into small networks, the 2 small networks, which are identified as subnets 16 and 32. To the outside world, or the other side of the router, these 2 networks still appear to be a single network identified as 144.28.0.0. So, for example, if the other side of the router considers the device at 144.28.16.22 to belong to the 144.28.0.0 network, as a result, a packet sent to this device will be delivered to the router at 144.28.0.0. Then the router would consider the subnet portion of the host ID and decide whether to route the packet to subnet 16 or 32. So, for subnetting to work, the router must be told which portion of the host ID should be used for the subnet network ID. This little sleight of hand is accomplished by using another 32-bit number known as the subnet mask. Those IP address bits that represent the network ID are represented by a 1 in the mask, and those bits that represent the host ID appear as a 0 in the mask. As a result, a subnet mask always has a consecutive string of 1s on the left followed by a string of 0s. So, for example, the subnet mask for the subnet shown in Figure 1, where the network ID consists of the 16-bit network ID plus an additional 4-bit subnet ID, would look like this. So there you have the all 1s in the right and 0s on the left. So the 1s now will represent the network ID, and the 0s would represent the host ID. So in other words, the first 20 bits are 1s and the remaining 12 bits are 0s. Thus, the complete network ID is 20 bits in length, and the actual host ID portion of the subnetted address is 12 bits in length. Since we all, if we sum it up together, it would be 32 bits, which is our address. So, to determine the network ID of an IP address, the router must have both the IP address and the subnet mask. The router then performs a bitwise operation called a logical AND on the IP address in order to extract the network ID. So, to perform a logical AND, each bit in the IP address is compared with the corresponding bit in the subnet mask. If both bits are 1, the resulting bit in the network ID is set to 1. If either of the bits are 0, the resulting bit is set to 0. For example, here's how the network address is extracted from an IP address using the 20-bit subnet mask from the previous example. So here, we have our IP address 144.28.16.17, which is converted to binary, that is 1001000 and 0001110 for the 28, and 0001000 for 16, and 000100001 2417. So here our subnet mask also is in binary. So if we convert it like the ones above in IP address, it would be 255.255.240.0. So from this binary IP address and subnet mask, we then perform the logical AND. So if we compare the first bit in IP address and subnet mask, which is both 1, then the first bit of our network ID would also turn to 1. And in the second bit of the IP address is 0 and the subnet mask is 1, then the network ID second bit would turn to 0, since if there is any 0 of the 2, the result would be 0. So here we can now see that our network ID is 144.28.16.0. So next, the subnet mask itself is usually represented in dotted decimal notation. As a result, the 20-bit subnet mask used in the previous example would be represented as 255.255.40.0. So as what I've said earlier. So there you can see the dotted decimal notation of our binary subnet mask, which is 255.255.240.0. So don't confuse a subnet mask with an IP address, because a subnet mask doesn't represent any device or network on the internet. It is just a way of indicating which portion of an IP address should be used to determine the network ID. So it would help us determine the network ID. So an IP address is the only address that represents our devices or network on the internet, not the subnet mask. So network prefix notation. Because a subnet mask always begins with a consecutive sequence of ones to indicate which bits to use for the network ID, you can use a shorthand notation, a network prefix, to indicate how many bits of an IP address represents the network ID. The network prefix is indicated with a slash immediately after the IP address, followed by the number of network ID bits to use. So, for example, the IP address 144.28.16.17 with a subnet mask of 255.255.40.0 can be represented as 144.28.16.17/20 because the subnet mask 255.255.240 has 20 network ID bits. So, network prefix notation is also called classless interdomain routing notation, or CIDR, because it provides a way of indicating which portion of an address is the network ID and which is the host ID without relying on standard address classes. So, this is our default subnet mask. So we have here our class A, B, and C. If we turn, also we have here its dotted decimal notation, which is for class A is 255.0.0, and if we turn it into the binary notation, it would be all the first octet would be ones and the rest octets would be zeros. So In class A, here we have our network prefix /8. And also we have here our class B and C as well. So next. So in subnets and subnet mask, we also have restrictions that has been placed. So here, the minimum number of network ID bits is 8. As a result, the first octet of a subnet mask is always 255. Since the minimum number of network ID bits is 8, if we convert the 8 bits into the dotted decimal notation, it would be 255. So next, the maximum number of network ID bits is 30. Why? Because you have to leave at least 2 bits for the host ID portion of the address to allow for at least 2 hosts. So if you use all 32 bits for the network ID, that leaves no bits for the host ID. So obviously, that won't work. Leaving just 1 bit for the host ID won't work either, because a host ID of all ones is reserved for a broadcast address, and all zeros refers to the network itself. Thus, if you use 31 bits for the network ID and leave only 1 for the host ID 1 would be used for the broadcast address, and host ID 0 would be the network itself, leaving no room for actual hosts. That's why the maximum network ID size is 30 bits. So next we have, because the network ID portion of a subnet mask is always composed of consecutive bits set to 1, only 8 values are possible for each octet of a subnet mask, such as 0 or 128 or 192 or 224, 248, 252, 254, and 255. So a subnet address can't be all zeros or all ones. The number of unique subnet addresses is 2 less than 2 raised to the number of subnet address bits. So, for example, with 3 subnet address bits, 6 unique subnet addresses are possible. So, that would be 2 raised to the power of 3 minus 2 is equal to 6. This implies that you must have at least 2 subnet bits. So, next. So now we will going to determine the range of IP addresses. So here we have our 8 bits, which are the 128, 64, 32, 16, 8, 4, 2, and 1. And also, we have here our IP address 198.125.71.55/20. The /20 represents our subnet mask, since it represents how many bits is our network ID must be. So here we have our subnet mask /20 converted to binary notation. So here we have it 255.255.240.0. So our network ID, which is extracted from our IP address and subnet mask. So first, since our subnet mask is 255.255.240.0, our first and second octet would stay the same since it is all the bits are turned on. So there we have our network ID and broadcast ID 198.125. And now we're going to determine our third octet. Also, in our fourth octet, it stays the same since they are all in zeros. We don't have to change anything about it. And since it is said that in broadcast ID, all what's zeros will be turned to 1, so there we have it as 255. So now what we see under network ID is our result when using when performing the logical AND operation. So there, if we will compare the subnet mask 1 and network ID 0 in the third octet, it will turn to 0. If the second bit of our third octet of subnet mask is 1 and in network ID is 1, it would be 1. And the third bit of our subnet mask is 1 and our network ID is 0, then it would be 0 and so on and so forth. So now, our network ID, if we will convert the third octet into the dotted decimal notation, it would be 64. Since here we can see 0, 1, if we will put it here above, we can see that 1 is placed under the 64. So now, our third octet would be 64 since it is the only one that is turned on. So now we have the 64. Now to determine our third octet of the broadcast ID, we will going to see the last bit of our network ID. And now we have the 64. So in broadcast ID, we are just going to add the last bit, which is 64, and subtract it to 1 for the allocation for the host ID or the domain. So 64 plus 64 minus 1 would be 127. So now we already have our network ID 198.125.64.0 and our broadcast ID 198.125.127.255. So now we can easily identify usable IPs in our IP address. So if our network ID is 198.125.64.0, then our range would be 198.125.64.1 to 198.125.127.254 since it is in our broadcast ID. Now remember that you need to allocate 2 bits for the host ID and for the IP address. So next example. There we have it the same, our 8 bits. And our IP address, which is 172.156.91.100/22. Now, to determine our network ID, broadcast ID, and usable IPs, we will convert our subnet mask to binary notation. So there we have it, 255.255.252, if we will convert it to that dotted decimal notation. Next, so since the first the first two octets, are being turned on, all the 8 bits are turned on, then we will going to stay, we will not going to change anything about it. It will stay the same. So now we have 172.156 as our first and second octet. And also in our fourth octet, we will also change it to 0, since our subnet masks fourth octet are turned off. Then the 100 in our IP addresses fourth octet would also be turned off. So now we can determine our network ID. So since our IP addresses third octet is 91, there we have it, 91. And if we will compare the subnet mask and the network ID using the logical AND operation, it would be 010110000. Now, if we will convert it to dotted decimal notation, then it would be 88, since 64 plus 16 plus 8 is 88. So now we already have our network ID, which is 172.156.88.0. Now we can now determine our broadcast ID. So as what we did earlier, we will now determine our last bit in our network ID, which is the 8, right? 0 is allocated for 128, 1 is allocated for 64, 0 is for 32, 16 is for 1 is for 16, and the last 1 bit is for 8. So now we will do the same thing as what we did earlier. So 88 plus 8 minus 1 would be 95. So now we already have our broadcast ID, which is 172.156.95.255. And now we can easily determine again our usable IPs. So from our network ID, which is 172.156.88.0 are usable, and from our broadcast ID, which is 172.156.95.255, our usable IPs would be ranging from 172.156.88.1 to 172.156.94.254. So that is all for today. I hope you learned something about this video. Thank you.